In the previous video, what we went over is the Lorentz transformation, and we essentially wrote out a matrix form to do the transformations, where we're now writing things as covariant and contravariant vectors. And if you notice the difference between, say, the covariant, which we're writing with the subscript, that was just x0, x1, x2, x3, and the contravariant. So the difference for the Lorentz transformation is that there's now a minus sign on the CT, or the time component. And so what we could do is we could now introduce what's called the Minkowski metric. G mu nu, which is a minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It looks like the identity, but it has a minus sign in the time dimension. And so that means that what I can do is I can lower an operator. So x mu is equal to G mu nu, or now x nu. So if I start with a vector x nu that's contravariant, if I multiply it by the Minkowski metric, where all the indices are lower, I can lower it to a covariant vector. I can raise a covariant vector into a contravariant vector by applying G mu nu where the indices are up, x nu, like so. Okay. One thing we're going to be dealing with is these, what we call the invariant interval, which is essentially the dot product of itself. So you're finding the magnitude squared. So in this case, a mu times a mu is going to be minus a 0 squared plus a1 squared plus a2 squared plus a3 squared. So if we did this with our spatial, so let's say x mu is minus ct squared plus x squared plus y squared plus z squared. So that is our space-time interval. And the interesting thing is that this quantity here is space-like if that is greater than 0. So the spatial part is, so we basically get a positive interval. It is time-like if x mu times x mu is less than 0. So therefore the negative part of that statement above dominates, and it's light-like if it's equal to 0. Okay, so I mean, the math seems pretty straightforward. Your interval is either positive, negative, or 0. But what does that mean physically? Well, what most people do is they draw out what's called a space-time diagram. And what you get is, if I was to make a plot of time on one axis and space on the other axis, I would get, try and draw a little better than that. And then if you could do it, figure this as way the XY plane, what you would get is a cone like this. And what you find is that you're traveling now. If you're to map out all of your positions and times and connect them by a dot, you would walk along what's called this world line right here. And so now if we map out the regions inside this cone, you are space-like. And that means you could communicate with other world lines inside that cone with information, because that information can travel less than the speed of light. If you're outside here, in this region, that's time-like right here. So that matches with the fact that you get this negative value for the interval, and therefore any information here cannot make its way into the cone. It would have to travel faster than the speed of light to transmit that information. So instead, you would have to wait until this event at here eventually made its way into the cone, into the space-like region, for now be able to transmit some information over to my world line. Now, if you're light-like, then that means you are now traveling on this slope of here, or you're basically traveling at the speed of light. So that slope right there is c, the speed of light. Well, actually, probably 1 over c, because we're plotting it as t versus x. But anyway, so those are the different regions. You have space-like, time-like, and light-like. So you're on the light front of the cone. Okay. The other thing you can look at is, here you're below this x-axis, you're in the past. Up here, you're in the future. And if you're right on the line right here, then you are at the present. So every moment you are measuring right here on the axis, that is now. And the question is then, what's going to be in the future, or what happened to the past? You have to look inside the cone. But you can only get information out of what's inside the cone, because that's only in the region where the speed of light is, where velocities are less than the speed of light. Okay, so the next section to look at is relativistic mechanics. So we've pretty much gone over relativistic kinematics. We've looked at the time, we've looked at length, we've looked at velocity. Now we'd like to look at some other things in mechanics, like energy. So what I can do is kind of get us started off on this, and have to kind of define something called the proper time. And proper time is essentially the time measured in your rest frame. So when you declare yourself to be at rest, the time that you measure is now going to be considered the proper time. And we can define that proper time interval. We're going to use tau now for proper time, is the square root of 1 minus u over c squared dt. So this is, like I said, our proper time. And this is the time from another frame, which is moving with a relative velocity of u. So I've kind of switched from using v to u. U is now the relative velocity. So that velocity, u, is measured as the change in distance over a change in time, But these are ordinary velocities. Because I'm not using the proper time, I am using the time of the other frame. So instead, what I can do is measure speed with the proper time. And that I'm going to call eta. And that is measuring the same length, but now using proper time. And so this is what I would call the proper velocity. Okay, so now if you think about it, I just need to change the dt to a d tau. So that means my proper velocity is 1 over the square root of 1 minus u over c squared, or gamma u. Okay. Now, what's the point of this? Well, the point is that my proper time is going to be invariant. So the idea is that if I declare the proper time and I do a measurement, and you declare proper time in your frame, and you declare measurement, those proper times should be the same because we've declared our frame of reference to be the one that is at rest. So if we want to write this now in 4-vector notation, then, which I think we should start doing from now on, so eta mu is dx mu over d tau. So now if we're in 4-vector, we're going to get the x component, the y component, the z component, but we're also going to get the ct component of our velocity. And so why don't we look at that 0th component? So eta 0 is dx0 d tau, which is c dt d tau. So now I'm looking at the transformation from one to the other, and from our previous discussion, what we did is we wrote out c over the square root of 1 minus u over c quantity squared. Or essentially it's gamma c. So that is the, so this kind of makes sense because I declared this to be c dt. Okay, so that's the time component of my velocity, or the 0th component of the velocity. Okay, so what I could do now is to apply this to different terms, or apply the Lorentz transformation. So what I would have is basically the proper velocity measured in different frames. Like so. And I can write this out now as a Lorentz transformation, and mu is gamma mu nu n nu, where I don't have to write the bar anymore because the indices indicate whether or not which frame it's in, whether or not the mu frame or the nu frame. Okay, so I'm going to stop here.